my Lab 3. So the purpose of this experiment was to measure the distance dependence of the magnetic field due to a small bar magnet for both on-axis and off-axis magnetic fields. Another purpose is to compare measurements made with our smartphones to predicted measurements from a computer model in the Biot-Savart law. So first we found the location of our magnetometer chip in our smartphones using the maximum magnitude magnetic field in the y direction and the x direction and the minimum magnitude magnetic field in the x direction, and then flipping our smartphones perpendicular to the axis created by our meter stick to do the same for the y direction. And we place tapes there to locate it. It's important to make sure that every time you're calculating your magnetic field that you want to start from a zero total magnetic field. This is accounting for Earth's due north, and it assures that the only thing being measured is the magnetic field of the bar magnet. So the fundamental principles of this experiment was the Biot-Savart law, as mentioned before, and the distance-dependent expression, which will be used later to find n, while k is equal to a combination of constants and parameters. And the magnitude of this, the distance-dependent expression basically says that the magnitude decreases as the observation location is moved further from the bar magnet, which I did notice in my magnetometer readings on my smartphone. So this is just a visualization of what would happen if you had multiple magnetic field arrows, as you'll see later on in the coding section. And the white part in the middle is representing the bar magnet, while these are just the magnetic fields around the bar magnet that it creates. So these are my results from the experiment. Each R value at the top right represents the distance it took to get a magnetometer reading of 20 nanoteslas, and then 70, 120, 170, and 220 respectively. And the Excel sheet created a function, and it calculated the slope. And the slope here will be used to calculate my n later. Below is my off-axis field, which I found from finding the perpendicular distance needed to get a total magnetometer reading of 100 nanoteslas. And then it also calculated the x, y, and z components that was calculated to get the total reading of 100. The y coordinates did need to be corrected due to the Earth's magnetic field. So to do that, I subtracted the y component of Earth from my measured and got the y corrected component. And the Excel sheet also calculated my net in teslas. So my results, I found that my n was negative 2.6551 meters, and again this was used from the slope in the previous slide, and my magnetic moment was found to be 3.822 amp meters times meters squared. This was found from rearranging my previous equation from the first slide for B, and I used this negative 14.084 to equal my, it equals ln of B, and this 14.084 was found from my slope equation from the Excel sheet right here. And so I just rearranged the equation, and e to the ln is just going to return B. So therefore I solved for B and then multiplied by 4 pi, and I made the assumption that r is equal to 1, and mu naught is 10 raised to the negative 7, and there I was able to solve for mu. So from the observations, I noticed that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So this is the coding section. I first created a function for the magnetic field using the equation given for B, and then later I created 2 on-axis locations and 4 perpendicular axis locations using the distance that I calculated from the lab, and this is the code for that. And then I later created a visual for the 45 degrees off axis using the d perpendicular also calculated in the lab, and then it just created arrows to represent the magnetic field 45 degrees from the axis. So here is the conclusion of my code with the white cylinder in the middle representing the bar magnet. So if I hadn't orientated my experiment to compensate for the magnetic north, the values would not be an accurate representation of the experiment. And you know this because when you do compensate for the magnetic north, it essentially zeroes the magnetometer and assures that the only field being measured is from the bar magnet. And if you were to stick two identical magnets together end to end and run the experiment again, I would expect that the readings will be greater than that of just one magnet. Not necessarily double, but it would be larger. In conclusion, the distance dependent was calculated to be n equals negative 2.6551 meters, and the magnetic dipole moment was equal to 3.822 amperes times meters cubed. This was done by finding the slope of the function created from measuring the magnetic field from the bar magnet at various distances along with the Biot-Savart law. Thank you.